Hi, I'm Chiao-An from the Purdue University CS Department, presenting our work toward long-tailed online anomaly detection through class-agnostic concepts. This is a joint work with my collaborators Kuan-Chuan Peng during my internship at MERL and Professor Raymond A. Yin. We will present the following statement. We propose a new benchmark for long-tailed online anomaly detection, LTOAD. We propose a class-agnostic AD framework that requires no class information as input. We focus on anomaly detection, or AD, which involves identifying defect regions in a given image. There are numerous challenging settings in AD research. In 2024, LTAD explored the long-tail setting of unsupervised AD. The unsupervised suggests that there are only normal images in the training set. The long tail suggests that the training set is unevenly distributed. Without careful design, the performance drops between head classes and tail classes. The LTAD method pipeline can be simplified as follows. The image encoder encodes the input image X. The text encoder encodes the class C along with keywords describing the normality or abnormality of the class. The two features are then jointly fed into a predictor to acquire the final prediction Y. We want to extend LTAD to online settings where the model can continue update itself. However, LTAD is a class-aware method where they assume the class information C is given. Yet class labels are not available in online setting, and there could be unseen classes. Instead, a class-agnostic method is required. We learn a concept set to approximate the target class set. In online learning, our design can weigh images of both seen and unseen classes with existing concept modules. We assume that the class information C can be represented as a composition of multiple concepts in head C. For example, the class transistor is related to or derived from concept semiconductors and circuits. In other words, for each image of class C, we instead of applying a hard label, we assign a soft label. We leverage the zero-shot capability of foundation models where head C is learned with only visual information of the training set, or without seeing any class labels. At test time, a soft label or concept score P is assigned for each image. As shown in this example, our learned concept is quite accurate. Our class-agnostic model is based on the general two-branch pipeline of LTAD with key differences. The concept score P is assigned to each image X. P then controls the soft switching mechanism in our class-agnostic reconstruction module R and semantics module S. Since there is no existing benchmark for evaluating long-tail online AD, we propose our own design. The performance of an online algorithm is dependent on the data ordering. To test the robustness, we define 8 configurations with combinations of different session types, either blurry or disjoint, and ordering type, either head first, tail first, or mixed. For online learning, we propose anomalous adaptive learning algorithm. Our algorithm computes a pseudo-abnormal map and mass-dependent loss function. Since abnormal images in online training set are available in offline, we value potential abnormal samples more in the loss calculation. Finally, we use exponential moving average for more stable updates. Here is a comparison of offline MV tag in image level and pixel level. The column CA indicates whether a method is class agnostic or not. We observe that our LTOAD outperforms the SOTA on most settings while using no class information. Here's a comparison of the most challenging online configurations on MV tag. While the baseline falls off when the data distribution changes, our method keeps improving stably. We show that ours can adapt to unseen domains even if it is not designed for cross-dataset evaluation. For each experiment, we pre-train ours on the first dataset and evaluate on the second. Ours with online learning algorithm outperforms the one without. We hope this paper inspires more work on more challenging and realistic settings on anomaly detection. For more details, please refer to our paper. Thank you.